kind introduction and also to Celia for the invitation to join in the Ramon Margalef Colloquia. And my task today is to talk about coastal areas in a changing ocean, which doesn't say anything really, but then it gives me a lot of freedom to talk about whatever I want. But I will try to talk about two elements that are of significance for the theme of the course, which is living ocean in the past and future. So that's what I'm going to talk about, and I will first talk about the past and then focus on the future. And just on a note, then I have been balancing a bit my work, and on the last, I would say 5 years, I've been, while continuing to do what we might call fundamental science, I'm more active in areas of my research where I think I can make a contribution to improving the health of the oceans and improve the livelihoods of people. So I'm working on that area and then taking a step beyond science to also deliver action and translate the work that I do into tangible outcomes that can be beneficial in the real world for real people, not just for those who read research papers. So basically, I would like to first start by summarizing global losses in the ocean. So this is a summary of the losses of marine life. So we have about 20 species in the oceans have gone extinct. This is tragic, but it's very little compared to the over 4,000 or so on land that have documented to be extinct. But we have lost about 89% of the abundance of exploited megafauna, so that's vertebrates and other animals, and then most of the fisheries are overexploited, which means that the stocks are present in the ocean in a depleted abundance. And when we look at habitats, we have lost between 1/3 and 50% of the global extent of most coastal habitats that are of significance in terms of coastal protection, fisheries production, and also biodiversity support. So as a summary of this, we have lost about 50% of the blue natural capital of the ocean, and the blue natural capital can be defined as the components of the ecosystem that supports the processes that eventually underpin human well-being and a healthy functioning of ecosystems that can exist without human help, so they can be fully functional on their own. So basically the drivers of this loss have been 6 drivers. The oldest driver is hunting and also harvesting of marine life that accompanies modern humans on our path, because in the old caves where the oldest modern humans have been found, then they're also always coastal, and then we find shells and other remains of marine life. So they were gathering seafood, particularly abalone, and other mollusks that were collected from kelp forests. But then hunting became more industrious and eventually industrialized with the advent of the steam engine, and then which allow fleets to roam all around the oceans and also have refrigerators to bring back food and dead animals to from very remote locations. But hunting reached a maximum about 1970 or so, and then declined since. And the major element in declining of hunting was both two different pieces of legislation that were introduced in the 1970s and early 80s, which are the CITES Convention. There's the Convention for the International Trade of Endangered Species that was adopted in 1975, and the Whaling Moratorium of the International Whaling Commission that was established in 1982. So those two pieces of legislation then led to reduced hunting pressure, and now hunting pressure in the ocean is quite low. So compared to peak times. On the top, you can see some relevant, if you can read that, you can see some relevant pieces of legislation that were introduced, and also in the bottom, or changes that led to some changes in hunting. For instance, the hunting of whales. By the time the whaling moratorium was put in place, hunting of whales have already decreased, because the main reason for hunting of large marine animals like whales and also sea elephants and others, were actually hunting them for their oil. So we burned them in the streets. And last year I was in Glasgow in the COP26, and I showed a photo of a whale lamp, so a lamp in the street that illuminated the street with whale oil. And somebody went to the street that I showed, and the whale lamp is still there, but now it runs on solar power. So that's a positive story. But anyway, by the time then electricity was developed and electricity and gas were introduced as fuels for illuminating the streets, then the whaling reduced a lot. But by then, the stock of large whales in the ocean had already declined by about 90%. In the case of fishing pressure reached a maximum around 1990, and since it has gradually decreased by about 10% to date, and then it is increasingly regulated, and the number of stocks that are sustainably managed, the term sustainable is a loaded term, so it's changing over time, but sustainable in terms of fishing means that you can maintain a biomass that is able to sustain the harvesting process. So it doesn't have the social and economic dimensions that the term sustainability has now, but it was a term introduced in the 1950s with a specific mathematic meaning, which is what sustainable fishing means. So there's a decrease in fishing effort and pressure on the fish stocks in the ocean. It needs to decrease further, but the peak activity was already happened about 30 years ago. Then deforestation, which still continues in some parts of the ocean, was also a major change of impact to coastal areas, because full watersheds were deforested, and that led to the runoff of sediments and impacted on coastal ecosystems. For instance, working in the Philippines, in Europe, deforestation happened long ago. For instance, in Spain, it was mostly associated with the building of the fleets of Philip II and Charles I that deforested watersheds in Catalonia. For instance, at that time, so it's already many centuries ago, but in Southeast Asia still goes on and is recent. So in Australia, for instance, the deforestation of the watershed of the Great Barrier Reef that happened around the early part of the 20th century, then to be replaced by sugarcane, so the forests were cut down and replaced by sugarcane mostly, then led to all of the coral reefs that used to reach to the shore of the Australian continent being lost. So now you have to jump on a boat and ride for about 2 hours before you get to coral reefs. But earlier, in the early 1900s, the coral reefs reached all the way to the shore. So we've lost about 200 kilometers of coral reefs offshore. And that was mostly due to deforestation of the watershed. And in the Philippines, I've been working in areas that were recently logged. And there I could see modern coral reefs that were probably alive 10 years before I sampled them, that were buried below 1 meter of sediment. That had been washed down with heavy rains after the watershed was removed. So deforestation still continues, but across most of the world, deforestation has stopped. It remains a problem in Southeast Asia mostly, but in other regions of the world, forests are expanding rather than reducing. So again, peak probably was at the end of the previous century. And habitat loss also the same. So coastal habitats were lost due to replacement by other uses. Again, this is not a new phenomenon, but for instance, in the Netherlands, the reason why the Netherlands is about, on average, 4 meters below sea level is because in the 1600s, farmers built seawalls to block tidal flows in shallow coastal areas, and that's a process they call polderized. So they developed polders. And then when they dried up the land, then they used it for agriculture. But in fact, soon after the land was blocked from tidal flows, then the level of the land started to drop, first because the water content decreased, but also because the organic carbon stocks were released and oxidized. So most of the 4 meters of decrease in elevation are due to loss of carbon stocks. So that's 1600s, and it was done at scale, and the same occurred in China and other regions in Asia where seawalls were built to convert them into rice paddies and other uses, and again at the expense of destroying mangroves or salt marshes or seagrass meadows. So habitat loss still continues through development of urban areas and coastal cities and other infrastructure, but probably in the 70s is when this development reached a peak. So again, we are now past the peak of habitat loss. And unfortunately, on the other two vectors of impact, which are chemical pollution and climate change, we are still on an increased trajectory. So every year there's about 5,000 new synthetic chemicals that are produced by industry, and they are introduced in consumer goods and eventually entering the environment, with many of them creating impacts on the environment without industry really addressing that before they introduce them in consumer goods. So, and then plastic pollution continues to be a problem and continues to increase, although this year the nations that are members of the UN, which are all nations, then agreed to create a legally binding process to stop plastics from entering the ocean. And the first meeting of that process will be in Montevideo, in Uruguay, in November this year. In fact, I will be there. And then climate change, of course, is a main driver, which is not new. So probably around 1950, we can measure already evidence of impacts on the atmosphere, but the evidence of impacts from climate change and the extent of impacts has increased and continues to increase, and we have not yet managed to slow down this process, although there is the Paris Agreement in place that brings hope that if we comply with the Paris Agreement, at least we can contain climate change before devastating impacts are propagated across the world. So that's basically a narrative of what has happened mostly in the coastal ocean over the past centuries. For most of these drivers of change, we already are past the peak, so we touched bottom in terms of the impact some 3 decades ago, and we are now slowing down those pressures. So we can talk of 2 phases on the recent history of the oceans. One will be a phase of a rapid increase in human pressures that will start around the Industrial Revolution, but large-scale pressures already started before then. But then increase with the Industrial Revolution, then also with the great acceleration of industrialization after World War II, and now we're slowing down. So that slowdown of pressures then provides for an opportunity to slow down the pressures and set the conditions for recovery. So I would say that in the 21st century we have started a new phase in the ocean, which is a phase of recovery, or at least where recovery is possible. So I'll give you one example of how these legislations that are on the top eventually led to conservation successes. So if we focus, for instance, on the regulations and the laws that impact on hunting and trade of species that are CITES and the whaling moratorium, then that has led to marine mammals being now mostly in a recovery phase. And out of the 92 populations of marine mammals that are closely followed with high-quality scientific data, then 42% are increasing, and only 10% continue to decline. And these numbers are already from some years ago, so the numbers are a little better now. But when the whaling moratorium was introduced in the 1982, then that was actually due because one particular species, the humpback whale, was down to about only 200 animals in the ocean. And everybody thought that we were going to see them go extinct. So it will be one more of the 20 species that had been extinct. In fact, one of them, the stellar cow, is one that was driven to extinction by hunting. So it was a very large dugong-looking animal, 9 meters in length, that lived along the shores of Siberia and ate kelps and seagrass. So that was driven to extinction by hunting by Dutch hunters in the 1700s. So it seems like that was also the fate of the humpback whale. But when the moratorium was established, There were again about 200 animals left, but that has led to a rapid increase in humpback whales, rapid for an animal this size. So by now the abundance of humpback whales is estimated to be more than 60,000 animals in the world, which is believed to be above the abundance before World War II. So, and probably around historical abundance of humpback whales. So that means there's been a conservation success for this animal that was thought to be earmarked for extinction, and also many others have followed the same thing. So I mentioned elephant seals being hunted in the Pacific coast of North America. In 1906, there were only 20 elephant seals, called northern elephant seals, left in a little island in the Mexican Pacific, but again, a law was introduced that banned their hunting, and by now there is more than 250,000 elephant seals in the Pacific. And there's no sign that the small population size, that was about 20, has led to any bottleneck in genetics, so there's no evidence of any problems due to inbreeding or so in the population. And many of the whales are now on a recovery, or most whales are on a recovery trajectory, so we might recover the abundance of large whales by sometime this century. In fact, yesterday the World Economic Forum released a very flashy video, but it's work done by the International Monetary Fund that calculated the climate benefits of rebuilding the stock of whales. So in terms of carbon, one of these animals was calculated by the International Monetary Fund to be worth about $3 million just because of the climate benefits of a whale that keeps the ocean in a productive state, plus its own accumulates out of carbon that eventually goes to the deep sea when the animal dies. So now there's even awareness that rebuilding the abundance of whales is going to improve ocean productivity and generate climate benefits. So on this evidence, by maybe 20 years ago, I started to see evidence that there were symptoms of recovery in many components of the coastal habitats, whereas until during the 20th century, all of the news were about loss and decline. But gradually, news of success stories were being reported in the literature. So along with some colleagues, then we published a paper called Rebuilding Marine Life in 2020, where we summarized this evidence, and then we also looked how could we accelerate this process, and if it was possible to substantially rebuild the abundance of marine life sometime this century. So we actually concluded that it is possible to rebuild the abundance of marine life. That is going to take possibly about one human generation, which is about 30 years, to achieve this. So by 2050, it might be possible to rebuild the abundance of most components of marine ecosystems, the blue natural capital of the ocean that we have lost. And within this grand challenge for humanity, also an ethical obligation, because if we don't do it now, possibly 10 years from now, we will not be able to achieve this. So there's a window of opportunity to be able to do that, and if we don't act now, then we will be condemning future generations to an ocean that exists in a depleted state. And it's also very important for a sustainable future and the development of an economy that is built around positive biodiversity outcomes rather than deplete the oceans, which is something that I'm working on just now. So again, marine population trends are shifting from decline to increase across most ocean bases slowly. And then when we look at the recovery times, and this is a summary of recovery trajectories of different animals, including the humpback whale and the northern elephant seal that I mentioned earlier. So the one thing about life is that once you give it a break, then it comes up with an exponential growth rate. So it can really recover very, very fast. So it's like a spiral, because the larger the stock of one of population size of one species is, then the more it grows in absolute terms. So that once you set the conditions for recovery, that is really leads to an exponential process. And across most components of the ocean, and the recovery timescales from reported case studies is about 1 decade to 2 decades. So it takes about 10 to 20 years to recover a population of a marine species or a habitat once you remove the stress, except these deep sea ecosystems take significantly longer to recover, and in some cases, then we have never observed recovery. So we don't know, the longest studies are about 60 years, so for some habitats, we don't know really what the timescales are because we have not been tracking them for long enough to observe recovery. And I'll give you one example of this, which is about mangroves. So the extent of mangroves around 1940 was about 215,000 square kilometers of mangroves. Now we have very good data on global abundance of mangroves because they can be tracked very easily from satellites since 1980s or so. So the data are very reliable. But we also know that there were larger mangrove extents before 1915 that have been lost long ago. So particularly in Bangladesh and also in Vietnam, there have been losses in the 1800s. So the historical abundance was somewhat above this value, but the first estimate that we have is about 215,000 square kilometers of mangrove. So they declined rapidly after World War II at a decline rate of about 2.2% per year, and this is 10 times faster than the decline rate of tropical forest. So very rapid decline. But then when we get to the end of the 20th century, then we see a slowing down of the losses, and then I have an estimate between 2000 and 2015 of only 0.3% per year loss, and now the most recent estimates indicate that they're really now more or less in a steady state, not being lost. So there are losses in some areas and gains in some others. For instance, in the Red Sea, we just published a paper this year that where we showed that the area of mangroves has increased by 40% over the last 30 years. And there are regions like the Red Sea where mangroves are expanding, and there's still a few regions where mangroves are being lost, but mostly now we're seeing more regions going into positive trajectories than negative ones. So the first effort to revert this critical trend was done in Vietnam. And in Vietnam, the U.S. Air Force destroyed about 2,500 square kilometers of the Mekong Delta forest. That is one of the largest mangrove forests in the world. In fact, the largest mangrove forest in the world is the Sundarbans. The Sundarbans is a World Marine Heritage Park that is shared between India and Bangladesh, and it's actually part, although many people don't know, is an important part of Western culture, because Rudyard Kipling, when he wrote this Book of the Forest, or I don't know how you say the original title, but Book of the Forest, in fact, that happens in a mangrove, in the Sundarbans. So the Royal Bengal tiger, the evil character in the book, is actually a marine species that lives only on the mangrove. And if you take an analysis of carbon, a bit of carbon from the Royal Bengal tiger, you see that all of the carbon comes from the marine food web. So a marine species, but all that book is actually in the Sundarbans. So many people don't know that it's a mangrove. So the U.S. Air Force destroyed this mangrove, and that's a photograph released from the files of the U.S. Force just about 15 years ago, where everything was burned down to the ground with two herbicides, Agent Orange and Agent Yellow, and then they also finished it up with napalm, with incendiary bombs. So there was nothing left. And in fact, one of my projects in the Mekong Delta was because it was restored by the Vietnamese people once the war ended, but they used only 2 species of mangrove that they grew in nurseries to restore the mangrove. But the project that we had was about where is the source of the other species of mangrove. So when we were walking there, and I took this photo in 1997, that is about the same place of that other photo, like 25 years earlier. If you were not a trained botanist, you would not know that you were not walking on a pristine mangrove forest. So it felt like a pristine mangrove forest, but you would note that there was a dominance of 2 Rhizophora species, and many others that should be part of the forest were still largely missing. So we roam around the whole watershed of the Mekong Delta to find where were the few trees that survived the American War, and were the natural sources of seeds and propagules for the species that were not part of the restoration effort, and we were able to find only 5 trees that survived the American War. So very, very small trees. Anyway, the Vietnamese people planted about 2,700 square kilometers between 1978 and 1998. At that point when I was working there, that the last time I went to the Mekong Delta was year 2000. We were not really doing that much work on climate-related issues or the climate benefits of restoring, although we were looking at soils and carbon. But I asked some colleagues in Vietnam to go back and calculate the carbon sequestered in this forest, which they did. And the carbon sequestered in the restored mangrove was similar to the carbon they sequestered in pristine mangroves in Vietnam elsewhere that had not been impacted. And in fact, when they calculated how much carbon had been sequestered as an outcome of this restoration effort, and that was after about 20 years after the restoration started, then the estimate was five full years of national emissions of Vietnam. So it was a very important contribution to climate action, even though that was never part of the reason why they planted the mangrove. I think that Oscar Serrano is going to tell you about blue carbon, so I will not tell you more about this, but this is one of the benefits of restoration. And then the second major driver of awareness of the importance of mangroves. The reason why the Vietnamese planted it was basically for food security, because they were aware that the mangrove is very important for food production, so that's why they planted it. Then in the 26th of December of 2004, then there was a major tsunami in the Indian Ocean that there were 250,000 people that died on that tsunami. And then it was evident soon after the tsunami hit these areas that where there was a pocket of mangrove between the village and the ocean, then the loss of human lives was nearly zero. So all the countries in the Indian Ocean then embarked on large-scale mangrove reforestations in India, in Bangladesh, and also in Indonesia and Thailand, again for coastal protection benefits, not for climate change, but that contributed also importantly to slow down losses and set the conditions for regrowth. So if we then summarize these trajectories, the current estimate is about minus 0.13% per year, but when you look at the uncertainty, this is not very different from zero. So basically a flat trajectory now, but the conditions are set to increase mangrove reforestation, and now the main driver is blue carbon. So it's the awareness of the important role of mangroves in carbon sequestration that is driving blue carbon projects around the world. So if we achieve a 1% per year increase rate in mangrove forest, or 1.5% per year, then we can restore the former abundance of mangroves by 2050. And there are some set goals by international organizations that are more or less along these trajectories. And the major constraint is that in some areas, sea level rise is going to shift the habitat for mangroves inland, where the inland space is already occupied by human structures. So there's not enough accommodating space to achieve that. So we might not be able to fully restore mangroves to the former abundance, but we'll probably be quite close to achieving that by 2050. And another component of the coastal ecosystem, which is seagrass, had also been in decline throughout the 20th century globally. But then again, at least at the scale of Europe, recently we published a paper where we summarized trends of seagrass losses. You can follow the yellow line if you see it. So the green line is the net increase, and the red line is the net decrease, and the yellow line is the balance between the two. So it's the net rate of change per decade. So in the 1990s is when the changes in seagrass were highest, nearly 30% per decade on that particular decade, and that was due mostly to eutrophication, to the influx of excess nitrogen and phosphorus mostly from fertilizer application and agricultural and livestock fields into the ocean that deteriorated water quality and led to a loss of seagrass. But due to a series of initiatives in Europe, particularly first the Habitat Directive that protected seagrasses, then the Water Framework Directive that mandated countries to maintain good ecological status in the nearshore areas and included seagrass as a diagnostic element of that directive, and now more recently the Marine Directive. They have all been pushing the effort towards improving seagrass areas in Europe. So for the first time in the first decade of this century, then we have a net increase of seagrass area in Europe. That was about 12% increase, so not small, and in area that represents about 18,000 square kilometers of growth of seagrass. So we don't have newer data, but that's the first time that there's a trajectory shift from decline to recovery again with the 21st century. The main reasons of loss were water quality degradation. In the case of eelgrass, Zostera marina, one species was diseased that wiped most of the European populations in the Atlantic in the 1930s. Then also changes in coastal areas like coastal modification, mechanical damages and others. And the most important sources of recovery was active intervention, that is restoration, and then natural recovery of all colonization when the pressures were removed. So the problem with seagrass is that for mangroves, I mentioned we have very high quality data on the global extent for mangroves, but we don't have that for seagrass. So for seagrass, we have two estimates of the global extent, which is one estimate with high confidence, which is 160,000 square kilometers. High confidence means that this is the mapped area, but with lower confidence, there could be 100,000 square kilometers more, so 260,000. And then once I flew between Madrid and Miami, and I flew over this habitat that looks really amazing from the air, from the airplane. So you have a glare of blue, light blue coming from the ocean. That is the Bahamas banks. That is the largest carbonate bank in the ocean. That is 150,000 square kilometers, and where, for instance, seagrasses have never been mapped. So I was adamant that this must be the largest seagrass habitat in the world, but it cannot be mapped from satellites alone because the carbonate in the seafloor gives a high reflectance. So it's a high reflectance of light that gives this turquoise color. This actually is a photograph taken by a NASA astronaut that gave it to me, so I used it last year on a TED Talk. But it's from somebody called Scott Kelly. And he said this is the most beautiful sight of Earth from the International Space Station while he was there. So anyway, a very large area, very challenging to map. And then some colleagues from NGOs in Bahamas have done already about 2,100 scuba dives, but they have only mapped 2% of the area. So how can you map this whole area if you cannot use satellites? Because the seagrass are covered by carbonate, and then you don't have a signal from them. So I partner with an organization called Beneath the Waves that works there, and they work on this guy, which is the tiger shark. And the tiger shark has a strong fidelity to seagrass meadows. So we instrument the animals, and we published a paper last year that showed that these animals spend about 70% of their time swimming in seagrass meadows, and they're much better swimmers than any scuba diver that I know. They don't take breaks on the weekends, they don't complain, and they cover about 70 kilometers per day, one of these animals. So we actually tag them. So last year I was tagging them, so that's me in the center, and this is a tiger shark of about 3 meters long. And then we place these sensors, which are 360-degree cameras, which are the first time that these are placed on any marine animal. And then you need a special software to analyze them. So you can actually see all around the animal. So in addition to see in which habitat it was swimming, we could see if it was eating something, we could see it was coming to the mouth, and the mouth opening and eating something, and also the movement of the tail, from which we can calculate the speed and energy used because we know the size of the animal. So we will release these animals and then let them go and swim and do their thing for about 2 days, and then these sensors had a little attachment string that was programmed to be released after 2 days. So after 2 days, this package floated up, send a radio signal, and then we'll go and collect it, and then we will look at the images. So this is more or less what you see. Oops, this should be supposed to be a video, yeah. So you see all of that is seagrass. So you see the head of the animal, and then you see but you can actually, using a special software, you can look all around the animal. So this is the forward look of the animal. So we use that to build maps of seagrass in the Bahamas banks, and these are the trajectories of the sharks that we tagged. And then where they were in the banks, then we quantified if it was seagrass or not, and then we use that to ground truth 4 different estimates of remote sensing and add to those estimates. So in fact, we have a paper that's about to be published probably next week in Nature Communications, where we calculate the extent of the seagrass to be between 57,000 square kilometers and probably up to 92,000 square kilometers, because we have 5 different estimates, but when we use from remote sensing, but when we use the ground truthing from tiger sharks, we actually push the estimate to 92,000 square kilometers. This area had never been mapped, so just remember that the map area is 160. So this alone adds 60% more to the known area of seagrass in the world, and there are vast expanses of seagrass area, for instance, the Maldives, and some other areas that probably have very large seagrass areas have never been mapped. So we don't know yet. The data we have is mostly biased to North America and Europe, but we don't know about these areas. So another element of recovery is certainly protection. So marine protected areas is a tool to recover marine life, but also they bring about a number of climate benefits. So realizing the importance of marine protection for climate action, now there's a rapid growth in the extent of marine protected areas. And then if we look at the growth of marine protected areas in a little animation, started in the 1960s. Oh, oops, that's supposed to be two videos. No, I don't see the video. They should be coming the. No, it was not. In any case, this is an animation, but this is the consolidated data that was behind the animation. The only thing is that you see points how marine protected areas appeared across the ocean, and also there was another one animating the restoration projects. But the figure in the left shows the total growth in marine protected areas. So just for noting, at the beginning of this century, in the year 2000, the total area of marine protected areas was only 0.4%. By 2019, we had about 7.8%. If we continue, we extrapolate this trend, then we reach 30% by 2030 and 50% by 2050. So many of you have heard about this 30 by 30 goal. I'm not very keen on the 30 by 30 goal because it might mislead people into thinking that if you don't get 30% by 2030, we have failed, whereas the important thing is the trajectory. So 30 by 30 is just one point in this figure, right? So if we have the right trajectory, it doesn't really matter if we reach 30% in 2032 or 2029. But we should also continue, because this 30 by 30 then sets the ambition to protect 30%, but we should go beyond that. And if we continue at the same rate, we might reach 50% by 2050. And also the restoration projects are growing exponentially around the world, and not only growing in number, but growing in scale. So for instance, I was in Bali on a G20 meeting 3 weeks ago, and then I learned of a really nice story where during COVID, Bali depends exclusively on tourism. So during 2 years of very tight COVID lockdown, they had zero tourism income, and the people were actually suffering from hunger, only being able to eat coral fish that they will fish from the shore. That was the only source of food, but they have no income and nothing to eat. And then a colleague of mine then convinced the Indonesian government to release a COVID relief package that instead of just paying people to be at home, pay them to be engaged in coral restoration. So during 5 months, there were 11,000 people that were paid weekly to participate in coral restoration, and then they planted in 5 months 75 hectares of coral. That is 10 times larger than the largest coral restoration project that also happened in Indonesia about 10 years ago, and that project took 5 years. So they did in 5 months what they had 10 times more than they had done in 5 months before, and the community was very happy because they had an income and could afford food and so on. They also increase the value of corals on the eyes of the community and conserving corals. And now there were lots of coral gardens in the bay that I was visiting, where people were growing corals for trade, but also they were putting 10 to 15% back in the ocean. So now Indonesia has announced that they're going to restore 1,000 hectares of coral, which is it's about 15 times what they did already by 2024. So the size and the scale of projects is growing. And then that means that our role is shifting from sources of impact to custodians of biodiversity. And I organized a group called Pan Environment during the pandemic, where we gathered observations on the responses of ecosystems to the human lockdown during the pandemic. And we published a paper last year. And in the paper we published with about 350 observations of responses of species and ecosystems to human lockdown. We have as many cases where human confinement was a source of negative impact as we have cases where human confinement led to improvements in ecosystems. And the negative impacts came from, for protected areas, the people that were doing the surveillance were locked down, and therefore there was a lot of poaching. People entered marine protected areas to hunt and fish illegally. So the role of people as custodians was impacted by that, but also many conservation projects were impacted. And many projects that had started more than a decade ago failed because of those 2 years of gap in the effort. So now we humans, traditionally we see humans as sources of impact in the marine ecosystems, but we are also increasingly playing a positive role and being custodians, and we need to be there doing the work and restoring habitats. So that means that we need to reconsider most legal frameworks, because the legal frameworks that are conceived under the conservation paradigm then always recognize humans as a source of impact. So the legal frameworks are designed to keep humans away. So now we need to have legal frameworks that are designed for recovery, and that have humans on the ground and allow and encourage humans to be on the ground, engaged in positive stories. So we have marine conservation successes across many elements. They're growing rapidly. So we have 39 records published of marine conservation success, and the growth rate is 12% per year. So every year, the international literature has 12% more cases of successful recovery that are across many elements of the oceans and across geographies. And then they're also across all types of economic regimes, from developing to developed countries, and they involve benthic habitats, vegetated coastal habitats, seabirds, and then the pressures that were removed were overexploitation, pollution, disturbance, invasive species, particularly important for seabirds, but also climate change, although climate change is difficult to stop and alleviate. And then we also map how these things differ across geographies. And 18% of the conservation stories resulted from unassisted recovery of ecosystems, which means that 82% require the active involvement of people in restoring the ecosystem. And in that effort, so scientists had a particular role, and they were involved in most of the studies, but also industry was important, and government was always necessary, because government gives you the permits to be able to be on the ground doing something. And local communities were also involved in some of the studies. So I'm going to jump this one, but anyway, so we have now an increasing number of success stories, some in very unlikely environment, like coastal megacities like New York and others, where there are significant conservation successes, which means that we don't need to stop in pristine areas. We can also extend marine conservation to urban areas and achieve this recovery across the world. And humans are now very important sources of success in conservation in the ocean, rather than only sources of impact. So thank you very much. And then I think there will be a discussion in the afternoon, right, of all the talks. Yeah.